Hi, today we are diving into chapter 3 of our material science course. This chapter, we will focus on properties, behavior, and applications of different materials, helping us understand how they function in various engineering and technological fields. Through this chapter, we will explore key concepts related to conductivity, insulation, and material classification. We will discuss how different materials interact with electricity and heat, and why some materials are excellent conductors while others serve as insulators. We will also touch on factors like resistivity, electron mobility, and energy bands, which are crucial for understanding material performance in real world applications. By the end of this chapter, you will have a solid foundation in material properties and their impact on electrical and mechanical systems. Conductors are fundamental materials in electrical and electronic systems, allowing efficient charge flow with minimal resistance. Metals such as copper, silver, and aluminum are widely used due to their high electrical conductivity, which results from their free electron mobility. The atomic structure of conductors enables delocalized electrons, meaning that electrical current can flow easily under an applied voltage. This property makes conductors essential in applications like power transmission, circuit boards, and electronic circuits. In this chapter, we will explore the physical properties, conductivity mechanisms in various technologies. We will analyze how temperature, impurities, and materials composition influence conductivity and discuss practical aspects such as resistivity, conductivity, optimization, and material selection. Conductors plays a critical role in modern and electrical engineering, ensuring reliable performance in systems ranging from household wiring to advanced semiconductor devices. The ability of a material to conduct electricity is deeply rooted in its atomic structure, particularly the behavior of electrons. Atoms consist of negatively charged electrons orbiting a positively charged nucleus, which contains protons and neutrons. The electrons in the outermost shell, known as valence electrons, as we discussed previous week, are responsible for electrical conductivity. In conductors, these valence electrons are loosely bound to the nucleus, allowing them to move freely under an applied electrical field. Understanding the role of subatomic particles helps analyzing why certain materials exhibit high conductivity while others act as insulators. Protons, being positively charged and much heavier than electrons, remain fixed in the nucleus, contributing to the atom's overall stability but not to charge flow. Neutrons, which carry no charge, primarily influence atomic mass and stability rather than electrical properties. As we proceed, we will discuss how electron mobility, band structure, and atomic interactions define the conductivity of different materials. The distribution of electrons in specific energy levels around the nucleus follows a well-defined pattern based on quantum mechanics. We also discussed it on previous chapter. Each shell can hold a maximum number of electrons determined by the formula 2m power of 2, where m represents the shell number. The valence shell, or the outermost electron shell, plays a crucial role in defining the electrical conductivity. Elements with few valence electrons, such as copper, with just one electron in its valence shell, tend to be excellent conductors, as these electrons can move freely under an applied electrical field. The arrangement of electrons in shells also determines how atoms interact with one another. In materials where the valence shell is nearly full, electrons are tightly bound, making it difficult for them to participate in electrical conduction. This is why insulators like glass and ceramics have poor electrical conductivity, while metals, which have loosely held valence electrons, exhibit high conductivity. As we progress, we will explore how this electron behavior in conductors, semiconductors, and insulators influences material properties in real-world applications. In materials with 1 to 3 valence electrons, such as copper, iron, aluminum electrons, are not strongly bound to the nucleus. This allows them to move freely when a voltage is applied. It all creates an electric current. In conductors, the weak attraction between valence electrons and the nucleus makes it easier for electrons to be displaced and flow through the material. This property is allows metals to serve as efficient conductors in electrical applications. The strength of conductivity depends on the number of valence electrons. Copper, having one valence electron, is an excellent conductor, as we discussed earlier, while iron, with two valence electrons, and aluminum, with three valence electrons, have slightly lower conductivity. When voltage increases, electrons gain more energy and move faster, increasing the flow of current. Electrical conductivity is a fundamental property that determines how well a material allows electric current to flow. According to Ohm's law, the voltage across a material is proportional to the current flowing through it, with resistance acting as a proportionality factor. The resistance of a material depends on its length and cross-sectional area, with resistance increasing as length increases and decreasing as area increases. To better characterize materials, resistivity is used, which is independent of the sample's dimensions. The reciprocal of resistivity is conductivity, which quantifies how easily a material conducts electricity. Conductivity in measured ohm inverse, meter inverse, and material are classified based on their conductivity levels. High conductivity materials like metals, copper, silver, aluminum are widely used in electrical wiring and components, while insulators, rubber, glass, ceramics have extremely low conductivity. The ability to measure and classify materials based on their conductivity is essential in electrical engineering and, of course, in material science. Conductivity in materials is fundamentally determined by the presence and mobility of charge carriers, typically electrons. Materials with a high density of free electrons, such as metals, exhibit excellent conductivity due to the ease of which electrons can move through their atomic structure. The movement of these electrons is influenced by external factors such as applied voltage, temperature, and material composition. The key parameters used to describe conductivity include resistivity, which quantifies how strongly a material opposes the flow of electric current, and conductivity, which is the reciprocal of resistivity. Additionally, the concept of drift velocity plays a crucial role in understanding how electrons move in response to an electric field. Drift velocity is proportional to the applied electric field E and is defined by the mobility nu of the charge carriers. The higher the mobility, the easier it is for electrons to move, resulting in better conductivity. In different materials, conductivity varies significantly, with metals like copper and aluminum having high conductivity, while semiconductors and insulators have much lower values. Understanding these principles helps in designing efficient electrical systems and selecting the right materials for various technological applications. This problem requires calculating the conductivity of an aluminum alloy wire using fundamental electrical equations. First, we determine the resistance of the wire using Ohm's law, which states that voltage equals current times resistance. Given that the voltage drop is 432 millivolts and the current is 10 amperes, we solve for resistance by dividing the voltage by the current. This gives us a resistance value of 43.2 times 10 to the power of negative 3 ohms. Next, we calculate the resistivity, denoted by rho, using the formula that involves resistance, cross-section area, and length. The cross-section area is found using the diameter of 1 millimeter, applying the formula for the area of a circle. This results in a resistivity value of 33.9 times 10 to the power of negative 9 ohm meters. Finally, conductivity, denoted by sigma, is simply the reciprocal of resistivity. By taking 1 divided by resistivity, we obtain the conductivity value. In this problem, we are given the electrical conductivity of copper, and we need to calculate the density of free electrons in copper at room temperature. The given parameters are conductivity 58 times 10 to the power of 6 ohm inverse meter inverse, charge of an electron 0.16 times 10 to the power of negative 18, electron mobility 3.5 times 10 to the power of negative 3 square meters per volt second. We then use the formula for the number density of electrons. The answer is 104 times 10 to the power of 27 per cubic meter. In this problem, we need to calculate the drift velocity of free electrons in copper when an electric field of 0.5 volts per meter is applied. To do this, we use a simple equation that relates drift velocity to electron mobility and the electrical field. Drift velocity is found by multiplying the electron mobility by the electric field. The given electron mobility for copper is 3.5 times 10 to the power of negative 3 square meters per volt second. The electric field is given as 0.5 volts per meter. Now, multiplying these two values together, we get 1.75 times 10 to the power of negative 3. This means that under the applied electric field, the free electrons in copper move with a very slow drift velocity, about 1.75 millimeters per second. However, even though individual electrons move slowly, the overall effect of electrical conduction happens almost instantly due to the electric field propagating through the material. When we talk about conductive materials, we are referring to metals and other substances that allow electricity to flow easily. In electrical systems, conductors are used in cables, busbars, and transmission lines to carry current with minimal resistance. The lower the resistivity of a material, the better it is at conducting electricity. And this is important because lower resistance helps reduce power loss in the form of heat. Some of the most commonly used conductive metals are silver, copper, gold, and aluminum. Silver is the best conductor, but it's too expensive for most applications, so copper is widely used instead. Aluminum is another popular choice because it's lightweight and more affordable than copper, even though it has slightly higher resistance. Besides electrical properties, the cost of raw materials, extraction, and manufacturing also play a big role in deciding which conductors to use. In the next section, we will look more closely at how these materials compare in different applications. Electrical contact materials plays a crucial role in making and breaking circuits efficiently. These materials need to meet several important requirements to ensure reliable electrical performance. First, they must have good electrical conductivity to allow current to flow with minimal resistance. At the same time, the contact resistance should remain stable over time to prevent fluctuations in performance. In addition to electrical properties, thermal and mechanical characteristics are also important. The material should have good thermal conductivity to dissipate heat efficiently and avoid overheating. It should also resist oxidation and corrosion, as well as withstand abrasion and erosion over time. Contacts should not weld together due to high current flow, and they should show minimal material loss during operation. These factors help ensure long-lasting and efficient electrical connections in a variety of applications. Copper is a heavy metal with a distinct reddish color. It's highly malleable, meaning it can be easily bent and shaped into thin wire sheets, making it ideal for various industrial applications. Copper can be processed using both hot and cold methods, which allows it to be adapted to different manufacturing needs. When it comes to electrical properties, copper ranks second only to silver in electrical conductivity, making it essential material in power transmission and electronics. Additionally, copper is an excellent thermal conductor, which is why it's widely used in heating systems and electrical components. However, one drawback is that copper oxidizes when exposed to air over time. This oxidation leads to the formation of compounds that can hinder electrical conductivity. Despite this, copper remains a highly preferred contact material in electronics due to its balance of conductivity, flexibility, and durability. Gold is an excellent conductor of both electricity and heat. It's highly resistant to chemical reactions, which makes it one of the most stable metals in various environments. Unlike other metals, gold does not tarnish or corrode, making it ideal for long-lasting applications. However, pure gold is very soft and has a tendency to stick and boil when used in electrical contacts, which can cause performance issues in connectors and switches. Because of these limitations, pure gold is rarely used alone as a contact material. Instead, it is commonly alloyed with other metals such as silver, platinum, nickel, cobalt, copper. These alloys enhance the mechanical strength of gold while reducing its tendency to stick. This makes gold alloys a popular choice for high reliability electrical connections, especially in applications where corrosion resistance and long-term stability are crucial, such as aerospace and high-performance electronics. Silver is a soft metal with a shiny white appearance. It is the best electrical conductor among all metals, even outperforming copper and gold. This exceptional conductivity makes it an ideal choice for high-performance electrical applications. After gold, silver is also one of the most malleable and ductile metals, meaning it can be easily drawn into thin wires or shaped into various forms through cold working. Despite its advantages, silver has come some limitations. It doesn't react with air under normal conditions, but it is highly reactive to sulfur, acids, and industrial gases, which can lead to tarnishing. This oxidation layer can reduce its conductivity over time. Because of this, silver is widely used in contact materials for measuring instruments, switches, contactors, relays, and soldering applications, where its excellent electrical properties are essential, but protection from environmental exposure is also considered. Mercury is a unique metal because it is the only metal that remains liquid at room temperature. It has a silvery white appearance, and it's known for its high density and excellent electrical and thermal conductivity. However, its vapor is toxic, making it hazardous to human health if inhaled over prolonged exposure. One of the most distinctive properties of mercury is its high sensitivity to temperature changes, which makes it an ideal material for thermometers and barometers. It is also used as a contact material in electromechanical devices, such as tilt switches, where its fluidity and conductivity enable precise control mechanisms. However, due to its toxicity, the use of mercury has been significantly reduced in many modern applications. Pure water is a colorless, odorless, and tasteless liquid that doesn't conduct electricity. It acts as an insulator because it lacks free ions necessary for electrical conductivity. However, when acids, salts, or other dissolved minerals are added, water becomes a good conductor due to the presence of free moving charged particles. Water plays a significant role in battery and accumulator electrolytes, where it helps in the electrochemical reactions required for energy storage and discharge. Additionally, its boiling point increases under high pressure, making it essential in various industrial and scientific applications where controlled temperature and pressure are required. A thermocouple is a simple yet effective device used to measure temperature differences. It consists of two different metal wires connected at two junctions, exposed to different temperatures. The fundamental principle behind thermocouples is that when one end of the wire is heated, hot junction, and the other end is kept cold, cold junction, electrons may gain energy at the hot end and move towards the cooler end, creating an electric potential difference. This voltage is directly related to the temperature difference between the two junctions. The movement of electrons causes the cold end to become negatively charged and the hot end to be positively charged, generating a measurable voltage. This voltage can be used to determine the temperature difference between the two ends. Thermocouples are widely used in industrial, scientific, and engineering applications where precise temperature monitoring is required. This week, we covered the concept of conductive materials, exploring how metals like copper, silver, and gold efficiently conduct electricity due to their free moving electrons. We discussed their applications in electrical wiring, electronic devices, and thermal management. Additionally, we examined the importance of conductivity, resistivity, and factors that influence electron mobility. Materials such as mercury and water were also analyzed for their unique conductive properties, where thermocouples highlighted the role of conductors in temperature management. Next week, we will shift our focus to insulators, materials that prevent the flow of electrical current. Unlike conductors, insulators have tightly bound electrons, making them essential in electrical safety and energy efficiency. We will explore common insulating materials, their applications in electronics and power systems, and how they contribute to the overall functionality of electrical circuits. Stay tuned. Bye.